my Twitch streams.
Twitch says title is invalid. Twitch. All right. Well, hold on. Twitch is complaining at me. Let me fix this. Save. Okay. All right. We should be live. Cool. Okie dokie. Well, let's make sure.
Twinkle to your heart content now.
Yeah. All right. Go live. Let's see. Twitch says the title is invalid. Well, Twitch, you're invalid.
Oh, I just realized, ironically enough, the hoodie I'm wearing is an old Code Match hoodie.
Hey, I have at least 2 or 3 in my. Let's try this. Twitch says the title is invalid. Why? What is wrong? What's wrong with that title? Okay. All right. Title may conflict with moderation policy. It doesn't like Nougat.
Oh, I don't. It's that. I'm not even doing the Nougat talk.
That's the one you signed up for.
Well, I said I could do either that one or the understanding how your CPU thinks, and you never responded. And then I realized on my new computer I didn't have the Nougat server set up.
Oh.
Well, that's a shame. That's I guess that'll be my fault. I forgot to respond to the GitHub issue.
All right. Well, that means so which one are you doing?
Understanding how your CPU thinks.
That should still be a pretty good talk.
All right. Well, let's all right, let me do this. Twitch is still yelling at me. All right. And we're perfectly live. So I'm adjusting all this crap on live. All right. Okay. Come on, Twitch.
Now that just means y'all wait a couple months, and I'll come back and do the Nougat one.
Yeah.
We've got plenty of openings.
Yeah, after I set ProGit back up, because that was the thing, is I always ran ProGit in the background.
Yeah.
So I had everything internalized, and I never got around to setting up on this new computer I got a couple months ago.
You need to set up a Docker container for it.
I don't have Docker on here either. Which part of me is like, why haven't I put Docker on there yet? And part of me is fighting with Docker on my work computer right now.
Yeah, I think I mentioned this in the last .NET meetup to the previous speaker, but I use a Docker container called Portainer that has a web GUI to manage the Docker instance. That's been quite helpful for starting, stopping, managing containers.
Oh, Docker Desktop does all that just fine. The thing is because of the container we're trying to run, just about everyone on our dev team at work, minus my team, is all Mac OS and Linux based. And so they have a set of tools I need to get set up for something we're trying to do on my Windows machine. And so we're trying it as an experiment. Keep that in mind.
Yeah.
We're trying it as an experiment where we want to see if we can, instead of doing it through the old way through Git Bash, which was kind of janky, getting it through WSL2 in Ubuntu running native Linux. So that's what's causing the issues.
All right. Okay. I've tweaked as much as I'm allowed to tweak on my side. So, alrighty.
And the problem actually has more to do with WSL2 doesn't like networking. So I can get all the networking to work just fine in WSL1, but Docker for Windows, Docker Desktop likes WSL2 if preferable, but WSL2 really doesn't like networking right now.
Mm-hmm.
So it's kind of jumping back, and it's literally dropping to a command prompt, changing the version of Linux or WSL, fixing something, changing it back, trying something, and going back and forth that way. Because new technology.
Yeah. All right. Hello, everyone. Joining on the stream. I finally got Twitch up and running, so people should be coming in from Twitch. Hello to Alexander watching on LinkedIn. LinkedIn, which is absolutely, it's not the best streaming platform. So if you have the chance to move to YouTube or Twitch, you should probably do that. Alexander, just because you're going to get better quality on either of those. Thank you all for joining us. We are going to have a slightly different talk than we had been promoting. We'll get into that just in a second. So if you're hanging out with us, say hi in the chat. Say hi to my friend Disapproving Gorilla.
Yay, the disapproving gorilla.
It's a random draw every year. Do you get the room with Disapproving Gorilla? And this year I got Disapproving Gorilla, so I'm super happy. And everyone at home going, who the heck is Disapproving Gorilla? Well, I am at Code Mash in Sandusky, Ohio. It's a fantastic conference going on there, probably like their 12th year. I have no idea. It's been a while.
Something right.
Yeah, and they skipped last year because of COVID, and they are taking COVID precautions this year. So it's not as large of a conference as it normally would be, but it's still in person. And yeah, hopefully everyone gets something out of it. But the years and years and years ago, we gave names, like the collective we, the community, gave names to all the different paintings in the rooms of the Kalahari Water Park and Resort. So this is Disapproving Gorilla. There's another one that's like a giraffe, and then there's a rhino, and they all have nicknames. But the favorite is Disapproving Gorilla. Because if you look at it, like, hold on, I'm sorry, friends. We're just going to zoom in on Kevin here. Disapproving Gorilla is disapproving. Like, he's looking at you like, I know what you're doing in this hotel room, and I don't approve of it. I disapprove of it. So, Disapproving Gorilla. So, shout out to CTI Geek Stevens, who's here at CodeMash with me. He's not here in the room, but he's probably down the hall. So good to see you, Mr. Ed, Virginia. He approves of Disapproving Gorilla. I'm glad you approve. Flail Gracefully, thanks for shouting out the painting.
The Disapproving Gorilla has its own Twitter account too.
It does. I haven't seen him or her or they tweet this year, so I don't think they're here. Paul Chin, how are you, sir? Thank you for hanging out with us. All right. Well, I think we have a quorum. So hello, everyone. Welcome to the monthly HamptonRoads.net users group meeting. Welcome to 2020. We got here safely, hopefully. I'm glad to see you. I'm Kevin Griffin, one of the organizers. My better half is Drew, whose video is right below mine. Drew, thank you for hanging out with us today. And the guest of the hour is my friend Chris Gardner. I'm going to let Chris do all of his own introductions, but Chris also runs a conference, Dev Space, down in Alabama. And you're like right near NASA. So
Yep.
Any NASA friends, you should go down there sometime. And I think like when we weren't in COVID, weren't there like tours to NASA?
There
you
are
organized something, didn't you?
There are tours of the Space and Rocket Center, which has got most of the stuff there. You can't really get into Marshall Space Flight Center.
Yeah.
But you can get to see, and they've got all the relics and all the good stuff there. You can walk around the Saturn V. You can get up close with old some of the old space modules and all that stuff. So yeah, there's still plenty to do there. But no, you can't get into Marshall Space Flight Center.
Gotcha. So is that what they do at that facility is rocket development?
Yep, we're the propulsion systems part.
Okay. That's awesome. So Drew and I, we're near Langley, Virginia, which is the wind tunnels. It's also where they test they have the historic site where they tested the command module landing, so water landings and stuff like that for Apollo. That's a lot of fun. But you can go there and you can see the apparatus that they use to do all the testing.
Yeah, the Space and Rocket Center, the U.S. Space and Rocket Center, which is
that way,
10 miles that way, is part of the Smithsonian Institute, and it's like right in front of Marshall Space Flight Center. So you're getting most of the stuff, and like you can even see parts on the edge where it's like, oh, here's an overlook into the zero weight big water tank they do to test zero gravity. Yeah. Like you can see that, and if you go to Space Camp, which is in town, you actually in some of the advanced levels of Space Camp can get in there for a while. But it's kind of like there's an edge where this is the government side and this is the tourist side.
I want to go to adult Space Camp. That sounds like a ton of fun.
Yeah, and then
we were too poor to do Space Camp when I was a kid.
2 miles that way, roughly, is where they do all the rocket tests. So yeah, I hear them testing that stuff all the time.
All right. Well, that sounds like fun. So I know you said you're starting to plan, so maybe we'll hear some news in the upcoming weeks.
Yeah, I can leak our dates ish, but there's no official anything out yet. But we have solidified our dates with the convention center.
Oh, well, the dates. I should put on my calendar. I would love to come down. I've had conflicts like past several years. So when are the dates?
It's like second week of September.
Okay.
When we get to the more desktop part, I'll pull open the calendar and I can look at it and say the exact dates. But it's like second week of September.
Sounds good. All right, Chris. Well, we're going to let you get to it. I'm going to throw your screen up. So everyone, Chris, you have the floor.
Thank you very much. Hi, everybody. Welcome. I don't know how many people are currently in the room watching because I'm not watching that thing, but I am seeing your comments come up. So ask questions at any time, all that other good stuff. Hopefully I will see them, or if not, Kevin or one of them can pop up and ask. This is understanding how your CPU thinks. I know they thought I was doing the NuGet one, but I have a new computer and my NuGet server isn't set up yet, so that's on me. I'll come back in a couple months and do the NuGet talk for y'all. This is a good talk too. You'll love it. Everything's great. 2 seconds about me. The obligatory vanity slide, if the right thing will have focus. Next slide. There we go. My name's Chris Gardner. I am the chairman of the DevSpace Technical Conference. So there's our nice logo right there. Like I said, we're hoping in person mid or early September this year. We'll see how that goes. I'm also a senior software engineer. Because I work at an advertising company and brand safety, they asked me not to publicly say on the internet where I work. But if you're curious, hit me up somewhere. We're all good there. But you're not here about all that stuff. You're here to hear the other stuff. So let me give you a brief summary of how we're going to break this down. And then that'll kind of give context. I will give you one bit of warning. This is a .NET talk. It is indeed a .NET talk. Even though it is the beginning 2/3, so how the CPU works at a high level and how the CPU works at a low level are kind of agnostic. But then when we start talking about how the common algorithms work, which ties into thinking how the CPU works, so that's when we're talking about your language versus whatever. We're definitely going to get hit .NET there, and we're going to hit FSharp. Don't be scared. You're not expected to necessarily know how to write the FSharp. It's just because I had those algorithms written in that language. They're nice and short so we can see what we're talking about, and I'll walk through them. You'll be fine. It's good to see something new every now and then, right? So yes, first we're going to talk about the high level, then the low level, and then we'll talk about common algorithms. Functional is greater than object-oriented programming dynamic. You are 100% correct there, Asa. So the key takeaway, basically, though, is to give you all a basic understanding of how the computer is actually working. This will allow you to think like a computer and write better code. And I promise that is the last slide I'm going to read verbatim. So if I stick the landing, this is what you're going to take away from the talk. Wish me luck. So we're going to start by talking about the two most important skills for a developer. Normally here I would ask you what you all think it is. Typing over a web meeting I know sometimes can be difficult, so we're just cut straight to the chase. Feel free to put snark in the chat all you want. I enjoy a little bit of ribbing at all points in time. But the first part is you have to be able to break problems into smaller problems, right? So you're given this huge set of requirements. You got to be able to take it, break it down into smaller parts, break those down into smaller parts, keep going until you eventually hit small enough chunks that you can actually write, and then you build everything back up. But the second most important skill as a developer, which I think a lot of people underappreciate, is communication, right? We have to be able to talk to the members of our team. We have to be able to talk to the project owners. We have to be able to talk to our upper management. We have to be able to talk to customers. All of that stuff, communication skills, in my mind, are almost more important than the programming skills if you want to be effective in your job. But let's dig a little deeper inside of that idea of communication, because yes, you do have to be an interpreter where we have all the upper end knowledge of how the computer works and how the languages work and whatnot, but we really can't just push that forward with and do all this techno jargon to our boss, who may just be a pure manager, or somebody who's up in that, or the customer who just wants something that works, right? We need to be able to take those skills and say, well, here's the problem, and break it down into a way that they can understand. So there's this real interpretation between the more rigorous language we use when we're talking to each other to the softened language we use when we talk to our customers and less technical people. But on top of that, we're also a interpreter to the computer, because we have to take all these fuzzy things that come out from our users and our customers and the stakeholders and all that, and we have to rigorously define them in a way the computer can understand so it can execute these languages. So much like when you're talking to a person, you need to understand how to take your formal thought and make it right for them. Just same way with the computers, you have to figure out how to take your formal thought and formalize it to them. Like any interpreter, the better you understand how their language is working, the better you can express to them in their language what's going on. And I think this is something that's really, in a lot of ways, through, and I'm not making fun of boot camps, I'm not making fun of degrees, I'm teaching a college class right now. I think this is something that we really don't think about, that we're speaking to the computer, we're giving it instructions, and we need to understand how it's operating, almost in a personification way. I have never met a senior level program that doesn't talk to his computer. All I'm saying, it's their best friend. They get in fights all the time, but it's there. So how does a computer think, right? What is going on inside the processor from a very high level? Well, it's time for an analogy. Hopefully this isn't the worst analogy ever. People have told me it's pretty good, but we're going to go for it. So compare yourself to the computer. We're going to compare you, the programmer, to what your computer's doing. I love this this tweet. I've got it linked down here in the bottom. I don't know if you all can see my mouse. Yeah, it is showing. I've got it linked down here in the bottom. I'll try to pop it into some sort of chat or something if I can later, or I'll retweet it. But it really breaks down, and the reason I like this, the difference in speeds between what's going on in the computer and what's going on to a person. And I love it because it starts at 1 CPU cycle, and it says 1 CPU cycle to an average person has a latency of 0.3 nanoseconds right? Super small, and that can be scaled to 1 second for a person. And the reason I like, well, it just says scaled, but the reason I like the fact that it goes to 1 second is because if you think about the caliber of things your average computer can do in one CPU cycle, one of those things is add two arbitrary numbers. So if you give it two integers the way it's normally going to do it, it can do a simple addition exercise. It can have something in a register, and we'll talk about registers and all that in a second. It can pull something from a register, have something in the accumulator, drop the answer back out. It can do all that in one clock cycle. But as you sitting there as a person, if I were to sit out here and randomly throw out two arbitrarily simple integers, like 5 and 3, it would take you about a second for that to hit your brain, you to, interpret those numbers and be able to spit out 8. So it works as a really good scaling factor. But then as we go up, you see how tasks take slightly longer, and then using that scale, it comes out. And then some of my favorite things that come from this is, as we're going through the different levels of caches, it shows how longer this takes, 0.3 seconds for a level 1 cache. Okay, it's a slightly bigger number, so you got to think about it. You're not using that automatic reflex. All of a sudden, you jump to a level 3 cache. Oh, I'm going to need a calculator for that one. You got main memory access. Oh, that's a sufficiently complex math problem. I may need to write down some substeps or something. And then when it gets really fun is when we start talking about network access, and like that 40 millisecond ping time everybody loves in this scaled example is like 4 years. So think about it. Okay, so for the computer, it's taking 40 seconds to go from New York to San Francisco. Were you to walk that across the country, yes, you could probably beat 4 years. But, these are the type of time frames we're talking about. And then my personal favorite down here at the bottom, if you do a physical system reboot, yes, 5 minutes on an old server, that's like 32 millennia to us, But let's take this analogy further, right? Let's talk about processors. So we've got physical cores and virtual cores. And you'll hear those come up all over the place. Our virtual cores are like if you have a single computer and you've got 6 monitors. So you've got one processor doing all the work, but it's got 6 things actively going by sharing things or by having little things, but it's all in the same chip. You can also have physical cores, like what's showing up in this other picture right here, where each one of these screens is its own computer. There's another one right here that can't really be seen. There's another one over here that can't be seen. There was one over here that can't be seen. A fun fact, if you're really paying attention, that PowerPoint presentation on that monitor is this slide deck with this picture in place while I took this picture with my camera. Just, fun fact. My desktop setup doesn't look like that anymore, but it looks remarkably close. But these, each one can concentrate on one thing that's showing up, and so you're getting more performance, but you don't get the ease of them being able to talk together as easily because they would have to share information back and forth. With this setup that I'm using on my desktop, there's no application I'm using to share my clipboard across the machines. I do have network access where I could drag a file across and pull it up on the other side or anything like that. But they're separated and they can completely isolate on a task. Whereas here with the virtual cores, it's having to either use the separate virtual cores or it's doing some sort of hyper-threaded time-sharing technique. So, same thing like you working normally. Let's talk about pipelining. So pipelining's been in computers for a very long time. And it's the idea of this is one of the first big advances back in the 90s-ish when computers sped up, was that it took that way it performed tasks, because every time a computer performs tasks, it fetches the instruction, so it goes to see what it needs to do. It looks at the instruction manual, thinks about it, says, what all do I need to do that, does that step, and then puts the result of that step somewhere so it can read the next one. So pipelining in the computer is what says, hey, I'm going to fetch this, Now, while I'm fetching this, now I can be decoding it while I've got something else that's running that's going to fetch the next thing, so it's sitting there. And then while I'm executing that, I can be figuring out what the last thing was while I fetch the next thing. So it does those 4 parts in parallel and pipelines them through. That's why it's called pipelining. Along the lines of the same time, much like you, let's say you're working on a ticket from work. So while you're working on it, you go and you get the latest version of the source code from Git, because maybe you hadn't been in the project for a while. And then you get that, and while that's building, you download the data set, because maybe you're working on a bug. So this is the particular data that will actually help you see what the bug is. And then after that's done downloading, you change the ticket to in process so you can start figuring out exactly. And you've got things executing in the background for you while you're still moving on steps so that you can keep things going at the same time. One of the things you need to worry about when you're writing your code, to bring this back to how thinking like your computer, is that the more linear your code is, the more effectively this pipelining works. When you've got things like weird branch statements, all of a sudden that decode didn't work or that fetch doesn't work. It may have fetched the wrong next instruction, or it may have or it may just wait to say, which of these 2 do I need to do? I need you to execute so I can see where I'm going next. So that will slow things down. Or when you start throwing exceptions, now you're not even remotely close to the code you were going to do. And these things slow things down, and it slows down the pipeline. So, the more solidly you can write your code and have things really go from A to B, and of course, exceptions are always going to happen. If statements are always going to happen. These things happen. But these are types of things that this is how your computer is handling it, and you can speed things up. Now, actually inside your computer, inside the hardware, we have these ways of storing things and whatnot. So we have registers. Registers are very limited, but they're the actual memory that's on the CPU. Right? That's the working memory of the computer. Extremely limited. We're talking, you're dealing with, if you've got a 64-bit processor, you're dealing with longs or doubles if it's an IEEE floating point number. And you've only probably got 12 to 16 of them really you can use on the computer. But they're extremely fast. Then on most modern computers, you have the caches. Most of the caches are on the CPU, but they're not in the CPU, so they're on that same chip. They just may not actually be. They're not actually in the part that's doing the computing. Most newer computers have up to a level 3 cache. As that number goes up, the size of that cache increases, but it's also how far it is. So it goes to fetch an instruction. It first tries to go to the level 1 cache. If it can't find it in level 1 cache, it goes to level 2. If it can't find it in level 2, it goes to level 3, etc. Each time it takes longer and longer because it has to go farther away. It's like saying, I have it right here at my desk. No, wait, I have it over here on this. No, I have it over here on this book. No, it's over in the living room. Right? That's kind of where we're going at with these caches. RAM, you know what RAM is, but RAM's the next thing up that step. It's got a direct pipeline into the processor, but it's got very, again, limited space, and there's a lot of stuff in it, so getting through it's not. And then storage is where everything else goes. It's where you hide. It's super slow, especially if you're dealing with hard drives, old school platters, rotating disks. As you're getting, and this can go on, hey, I have to go to the network for this. As we go on. But with our analogy, let's compare this to you. So I've got Visual Studio open right here, right? Everything's doing good. So right here, the big red box right there, that's like your register. It's a very small subset of the code, and it's your working memory of what you have direct access to right now, that little bitty snapshot. Fun fact, we're going to come back and talk about that code later, that exact code, when we start talking about some of the algorithms and how things work. Don't worry about understanding it now. So once we get past that, we have our level 1 cache, which is the scroll bar. So from there, we can very quickly go up or down within that same file, and we can access things. It's not quite as fast as having it on the screen, but it's already completely loaded in memory. It's completely ready to go. We can get to it really quick. hotkey searches will get there fast, all that other good stuff. That's our next step up. Up here in the document bar, we have our level 2 cache. These things are rip-roaring and ready to go, but to use them, you need to go over and either, control tab over to them or move your mouse open and select the individual one. The program's got to go. It's got to render that file up. It may not be in the right place in the file. You may need to scroll from there. It's there. It's convenient. It's open. Not quite as fast. Over here in the Solution Explorer, you have your level 3 cache, right? These are available for you to get to these files quickly. However, if you hit that, it's actually got to go open the file, so you're going to burn some time there. But you can get at those files very quickly because you're saying, hey, keep track of these. I may want to get a hold of any of them at any particular point in time. As we get a little further out, if we come down here, I've got all these applications open. This is like my RAM, right? If I really need to, I can go down there and click one of those. But now we're telling the processor, hey, I need you to do a context switch. I need you to take the program I'm running. I need you to put it kind of in stasis. I need you to grab this program that's in stasis. I need to pull it back out. I need to refresh it so it now takes over everything. And so there's that kind of context switch, and then it slows down what's going on, all that other stuff. So that's your random access. And then everything else down there in my quick bar, that's all my storage. I can get one of these if I really want to, but it's going to waste some time because now I've actually got to open the thing. Furthermore, even though I didn't put it on the slide deck of all this, I could go into the Start menu. I could go find something that's actually on my computer. I could open up File Explorer. I could go manually searching for things. Now you're talking computer terms. That's kind of like network access. That's okay. I have to go way out of the way, get something, bring it back. That's when we're starting to talk about that. Any questions with that? Does that make sense to anybody, to everybody? Is there any one part of it you need me to take a second to explain a little bit better? Or are we good? I'll give, take a sip of my liquid and give a minute or a few seconds to see if somebody wants to pipe up with something. No.
Things are pretty quiet in here.
Sounds good. All right, let's keep moving. Furthermore, let's go deeper. Let's take that leap of faith. So now we're kind of done at that high level. We're going a little bit lower. Really good analogies. I appreciate that, certainly, Deb. Thank you. Let's go a little deeper, taking our leap of faith further. And let's go inside the CPU. And I really love this analogy of talking about a byte as a string of light bulbs with 1 and 0s. Because for those of you that don't know, inside your computer, everything's binary. But the way that's tracked is either by 0 volts or 1, or 0 or 1 is tracked by no voltage or 5 volts. So if it's a 1 down that data path, it sends 5 volts. If it's not, it sends no voltage. And because these things are pushing so much electricity so fast, which is why heat is a major problem, as all the electricity going through and the resistance in the wires and all that, there actually is a tolerance. Anything below 1.3 volts is considered a 0. Anything between 3.7 and 6.3 volts is considered a 1. And if it finds a voltage between that, that's when you start getting blue screens. If you hear people talk about power conditioners and dirty power, that's where all that comes from. But it really is a matter of, I'm sending no electricity, I'm sending electricity. And you put all those together and you magically get a number. So you write the fundamental lie of computer science. This is indeed the fundamental lie of computer science. I have been teaching at universities for many, many years. I have had the pleasure to teach Intro to Programming. I tell all my students, you see this right here, x equals x plus 1? If this makes you squirm, there's time to jump now. Here's the fundamental lie of computer science. We just set something equal to something that it's absolutely not equal to. Because, of course, that's assignment to us, but I have seen math majors squirm at that and not want to go any further. So you write the fundamental lie of computer science. And this is any language you want it to be. I think specifically this is written to be C code, because for the next few examples, everything is compiling down like that. More on that in a second. And by a second, I mean 1 Mississippi. So when you write that, this is what your compiler writes it when it deconstructs it down to assembly language. So the C compiler goes and it writes this out, and this is the assembly language it looks like. This is the exact assembly language for an x86 processor for that code. It's what it's going to look like. We're not going to go too hardcore in this. This is not about actually being able to read assembly language, but push, that's sending a value in. We're going to move some stuff around all through here. Here's where we're adding the value that came in to the constant 1. We're going to put the result somewhere. Pop means we're going to return the value. That's basically what it's doing. Let's dig a little deeper than that. Right? Let's look at that particular line. We're going to add a D word pointer here. So we're going to say add the value you find here and the number 1. That's what we're doing. That is the simple addition that the computer can do in 0.3 nanoseconds. That's the line of instruction. That's what we're saying. What do you think the computer sees? Oh, it's going to get ugly. That's what the computer sees, right? That's what's in the memory. Okay. Let's not panic. Let's break down what all of this is, right? This is what actually is going on in the computer. Encoded as this is what we call an opcode, and then there are parameters. So the CPU gets this whole ugly thing, which we're not going to worry about too much. I don't even know where the correct boundaries are right here. So don't ask me. Yes, I found a website that would take a line of assembly language and give you the actual machine code for an x86 processor. I did not try to understand it. Some things aren't worth that much. But basically what it's doing is some of the first part here, I don't know how far it goes, is what's called the opcode. It's the same thing as the method name when you're writing a program. It's saying, hey, this is the operation we need to do. Inside that opcode, the computer knows, oh, well, if I'm getting this operation, much like your compiler, I need this many parameters of this type, right? So it knows that. It figures out how many parameters it needs. It then goes and pulls off as much memory as it needs to get the next part of it, which are to get the parameters. It then performs those actions and stores the results as binary again. Everything goes on, right? So it's saying, hey, I need you to give me 16 bytes. Let's say it's a 16-byte instruction set, or 16-bit. So give me 16 bits. Oh, I see that means I need to add. So I need a memory address to go get memory from, and I need the number you want to add to it. There's that one. There's that hard-coded 1. I know that much. This is some sort of reference to a memory address. Go get that value, come back. That's what's really going on inside of it. It's no different, for those of you who have done it before, as writing a program with command line parameters. If you've ever handled command line parameters, written something that actually does it natively, void, main, args, string array args, actually handle them. You get the whole list of stuff. You loop through the first one. You grab the first switch from your list of parameters, which is like your opcode. You say, okay, I have this switch. That tells you how many more parameters you should expect. You may expect 0, you may expect 2, you may expect 1. Tells you what comes next. You then go down the array and grab the next correct number of things. You process whatever that goes. And then you go back to the command line parameters to say, is there another switch? Oh, yep, I do have something else to do. I'll process that to get everything initialized. And you keep going till you hit the end. If it's written correctly, correct number of parameters are there for all your command line switches. You've initialized the program, and it goes off to do that. If you've done it incorrectly, then at some point in time, it's going to go, hey, I was expecting another parameter. I didn't get another parameter. Program's going to crash before it even begins. It's probably going to throw up a help message for you. Same way the computer's doing it inside. So now let's really have some fun. If we haven't mentioned yet, I like going really deep into languages, and I have a weird definition of fun. And let's talk about how that actually works. How do we do binary addition? And it's actually so simple that it's trivial, right? So we have this top number, 1110, which is what? 14? Right? 2 plus 4 plus 8, 14. We have this bottom number, 0110, which is 2 plus 4, so 6. So we're going to add 14 and 6. So what do we do first? We add up, just like we do in regular math, we add up the 2 zeros, we get a 0. All right, so we go to the next digit, we add up the 2 ones, we get a 0, because we can only go 2 places. So we go from 1 plus 1 is 2. Well, 2 is done as 1, 0, so we put down a 0 and we carry the 1. Cool. 1 plus 1 is 3, so we drop down a 1. We carry the 1. So far, so good. 1 plus 1 is 2. Well, that's 1, 0. So we drop the 0, and we carry the 1, and then that 1's just going to come down, right? If you ever have wondered how your computer knows when you get an overflow exception, we have a 4-digit number and a 4-digit number, and a 5-digit number came out. The fact that this overflow, it can track that this overflow bit came out, and that's how it knows your operation overflowed. Same thing when you do subtraction, it's still going to end up kicking out an overflow bit. That's why it knows that happens. Yep, the set carry flag. Yeah, and more specifically, we're going to get very much in detail with that. But you are 100% correct, Mr. Ed. It is the set carry flag. And the reason it's a set carry flag is because how do we do this? Everything inside the computer is binary logic. It is Boolean logic. It is trues and falses. It is ands and ors and XORs and nots. All that good stuff. Everything inside the computer is done that way. If you go really deep, you can hit classes and stuff where you actually have to say, here's a number and a number. How do we do this with Boolean logic so that the numbers come out correctly? How do you do it with multiplication? How do you string together these operators to do that? Truly with just anding and oring ones and zeros. So just like the number we just did, you would use a 4-bit adder, which is going to, up here at the top, take in the first 2 digits, kick 1 out, second 2, kick 1 out, third 2 digits, kick out. And you notice here at the very end it says, oh, well, we also have this carry out or overflow bit. That was the set carry flag, because if you need to calculate a 6-bit number or an 8-bit number, let's say, you can have 2 4-bit adders and just pass that carry out overflow into the carry in of another one. And then it will just do a 3-digit here and everything's fine. But this is it doing that operation we just did by hand completely in logic. And no, we're not going to break down exactly what it was. If you want to have some fun with this stuff, a couple of videos you can look up. Go to YouTube, look up Stand Up Mass Domino Computer. Matt Parker actually made a computer with dominoes where at the beginning there were 4 lines coming in and 4 lines coming in, and he had some way to trigger all of them at the same time. But for the ones and zeros, he would remove a few dominoes for the zeros, but it would come through and knock over all the dominoes. And he did all those logic gates completely with dominoes. Really interesting video. It's kind of long. It's like 22 minutes long. But it really shows how all those individual pieces work if you're really interested. Also, if you look for Steve Mold water computer, Steve Mold here actually made a computer that used water, and all these individual little things are various logic gates that filled up with water, and then would, whether or not the water came back out the other side, would determine on if it was a true or false. They're pretty interesting to watch. I enjoyed them a lot. I think you could actually learn a lot about what's going on with those logic gates that way. But keep in mind that your computer, when it says 14 trillion transistors or whatever they're up to now, transistor is a really fancy way of saying logic gate. Pretty much. Right? It's using that many pieces of logic to be able to put everything together. So, where does all of this come together, right? How do we get all these pieces together, etc., etc.? Ben Eater has a good 8-bit computer series. I will have to check that one out. And you've seen someone build a CPU in Minecraft. Yes, there's also one, if you look on YouTube, somebody created a computer in Mario Maker. So in Super Mario Maker, they have it at the beginning where you kick a couple blocks to set the initial bits, and then you have to hit something that tells all of those to go at the same time, and you jump on something, and it goes all the way through. It's absolutely incredible. And I was about to say my web browser just did something funny. Okay, we're back. There are lots of people doing computers in really weird ways. I'm actually playing around in my head, because I'm a dork, a way to make a computer with a hose. So it's also a water computer, but instead of using a gravity system, it uses a forced water system, just to see if I could do it, and the fun and interest of how do you create the logic gates with flowing water that way. It can be done in lots of different ways. Challenge yourself. So how does this all come together? So the reason all of this is, let's really think about our algorithms and how certain things come together. So let's drop out of the slide deck for a second. And here comes the dreaded FSharp, I promised. Sorry. So the background of this project, I work on it on Twitch sometimes. It's on GitHub if you want to look at it. I came up with the idea of why do we have to have fixed limits on the size of our numbers, right? Why do we have to have upper bounds? And try to come up with a way to create data types that did not have up or downs. Spoiler alert, it worked, and I have them. That's also the genesis of where this talk came from, because I learned a lot about what's going on with these low-level algorithms we take for granted when I had to suddenly implement them all. So the way, and right now we're not going to go into, if you very carefully can see, you've got a big enough screen. We've got all the way over here, there's rational numbers. Over here, we're doing real numbers. Yes, I have floating point numbers that can get as big as you want and as precise as you want. Never loses precision. Those are very complex, and I would not throw that on anybody who did not ask. But for these standard operators, I started with the natural numbers. Let's go from 0 up to as big as possible. And the way it's implemented is basically, it's an enumerable. It's actually an FSharp list. But you can think of it in C# terms for more .NET people as it's an enumerable of numbers that we just chain those bits together. And then we deal with everything in batches. It's that one. We even can take there's the main constructor where it takes an FSharp list. Here's where it takes a sequence. That's a C# enumerable, right? I can take either. But the way it does is like, so for addition, the way it works, and this is not where we want to get complicated yet, but like with addition, the way all this works is I have this internal thing that does this operation and returns the result. But what I basically do, without going too deep into here, is I take all of the numbers and I normalize the two numbers that come in. So you got the left side and the right side of the plus side. I make sure I add zeros in front until the two lists are the same size. I then add everything in the two lists, and if it overflows, I don't care. I just completely blow that off. And then I stick a 0 in front, an extra 0 in front of all that. I then go through and I calculate which ones would overflow. And if it overflows, I keep track of that. I then throw a 0 in the back. And then I said, hey, if anything overflowed, go through this entire operation again. We do that because I actually do have a unit test where I found a case where an overflow would cause an overflow. It's very subtle, but it exists. And it keeps going basically until there are no more overflows, and then it returns the results. And then I get rid of all those extra zeros I put out front. But there's your basic addition. In 90% of the cases, it's an extremely fast operation, right? Even if we're dealing with a, let's say, 320-bit number. No, let's not say 320-bit number. Let's knock that down. Let's say we're dealing with 8 integers wide, because most computers these days, well, between virtual and physical cores, have 8 cores on them. How many do I got? I think this one's got 16. See, I got 16 here. We're only using half of it with this operation. It can spread out all that all that data across a couple processors, do it quick, bring it back in. If there were no overflows to deal with, extremely fast operation, right? You should never feel bad about doing addition in your code. It's never going to hurt anything. It's a super fast operation. Subtraction, it's basically the same thing, right? You just kind of, it's the same. It gets a little more complex because of the way we have to track the underflows and the cascading underflows. We can't just loop back through like before. And this one actually does throw an exception if it would have been less than 0 because that doesn't exist inside of a natural number. But it's basically the same thing. So how do you think we do multiplication? And I guess now, since we are not as much in a what's the word I'm looking for? In an interactive session, I'll just cut straight to the chase. We basically do it the same way we do long division or long multiplication by hand. So let me tab out one for the first one. Let's say we have one. Come on. Oh, is my numlock off? My numlock's off. Let's say we have 1 0 1 0, and then we have 1 1 0 0. Right? We're going to use those two numbers, 10 and 12, because it spans every case of every binary case, right? And we're going to take these and we're going to multiply them together, right? This is how we would do this. So the first thing is 0 times is we take the first digit and multiply it by everything across. So 0 times all that is going to be 0 0 0 0. No big deal, right? 0 times the entire top line is just going to be 0. We take the 1. We take the next one. It's going to be all zeros. 0 0 0 0, right? We're going to come that across. We're then going to take the next one. Well, that's a 1, so we're going to end up with the same number, right? So in here, we end up with 1 0 1 0. All that's fine. The last one, the bottom digit down there, it's a 1. So again, we're going to end up with 1 0 1 0. And now, much like you would with real addition, we're going to pad these out with zeros, where I didn't put it there already, but we're going to pad those out with zeros. We're going to add all that up, and as we come through it, we're going to end up with 1 1 1 1 0 0. Right? There's our binary multiplication. And so if we took 10 and multiplied it by 12, we'd get 120. If we actually took that down, we would get 120. That's how it works. Well, how do you tell the computer to do that? Okay. We've got this magic formula where basically I have to go through each bit, one bit at a time, basically, using shift operators and things like that and say, is it there? Cool. Duplicate the first one and then add everything up when everything's done, right? And then at the end, just sum up all those lists. It's doing the exact same thing as if you do it by hand. Yes, there are slightly faster ways to do these multiplication tricks, but I'm dealing with a way weird object here, so that's why we're kind of doing it the by hand way. This is super inefficient. So, sometimes use case wise, avoiding multiplication sometimes or doing things that can reduce the multiplication can be helpful, right? Because it's a pretty complex algorithm to actually multiply. If you look at the amount of time it takes to do a multiplication compared to the amount of time it takes to do a addition to a standard processor, there's kind of a big jump there. And that's the reason why. It's just got to do this type of stuff. At one point in time, I was working on a way to count the number of ones in each of the two numbers to make it more efficient. And then I realized that algorithm was taking longer than just to brute force it. Go figure, right? That's what your tests are for. FSharp also gives you this nifty ability to make your own operators. So we all know how to divide, and we all know about modulo, right? Give me the division result, give me the remainder. I kind of figured out while I was doing it that, and this one gets really complicated. We're not going to go too hardcore into this one. It is exactly what you think. It is the inverse of multiplication, but the way it inverses is very nasty. But I did figure out that division, a byproduct of division is the remainder, and a byproduct of calculating the remainder is the dividend. or the quotient. So I wrote a new operator that gave you both at once as a tuple. And then the independent ones just call that and just return the one it needs. But then I was like, well, then why not make it available? So yeah, my library actually creates a new operator. You're welcome, everybody. Yes, it works in C#. You just have to call it, you have to call it weird. But this one takes forever. And if you look inside reference manuals at the length of time it takes for a division operation to work, we're still in integers. We hadn't hit floating point numbers yet. A division to work as opposed to a multiplication, again, that algorithm gets a lot more complex inside. That singular operation takes longer. If you could do a couple minuses instead of doing a division, you can actually speed things up because this is complex. The only reason I brought up these two is because we wanted to get to the one that was like the grand finale. The king poobah, the absolute, how are you going to pull this one off? And this was a tricky one. I actually had to look up how to do this one, which was, we're dealing with numbers, so of course we need to be able to write them out, right? So we needed toString. And then to be nice, because entering these extremely huge numbers is not very intuitive with the tools we have to use, we also wanted to parse, where if you gave it a number, give me the string of the number, I'll figure out all that lists and stuff. And I had to figure out how to do this. This was surprisingly more difficult than you think. And there's a specific reason why I'm bringing this example up. Most of us aren't parsing the same thing over and over again. And that's good, because parse is a hugely expensive operation. We'll talk about parse first, because much like how we talked how subtraction and addition were inverse operations, and multiplication and division were inverse operations of each other, toString and parse are inverse operations from each other. Parse takes a string and gives you a number. ToString takes a number and gives you a string. All right, so they should have some sort of Drupal made up a good point, which is multiplying by a power of 2 should be relatively fast. Yes, if you're doing that, you can use shift operators, and then it's supremely fast. Because you can cheat the system, and if you look inside my multiplication operator, it does lots of shifts, which is all that powers of 2 is very fast. 3 whacks are shift operators in FSharp instead of 2 like it is in C#. But that's basically what the shift operators do, is they're a very fast multiply and divide by 2. But that is a very good point. Thank you for bringing that up. All right, so we're going to talk about parse first, because parse almost makes the most sense. How do you take this thing and pull off a digit at a time to actually be able to go? Well, we have the string. So what if we rip off the tens digit, take that character, figure out what number it is, and add it, right? So we got that. Now we can chop off that part and take the next number, convert it from that ASCII, that one single ASCII code, to a number, and then we just have to multiply it by 10 and add it to the old one, and just keep repeating this over and over until we build the entire thing back up. Super not efficient. In fact, I even have this subroutine in here where I do powers of 10. Yes, I know this is super efficient. That's why this is currently a local function, and it's also currently why I wrote a talk where I tell people not to do this. But what's going on here is that we take the string, we turn it into a character array, we reverse it just because it made the math easier. This map right here basically says take all of those characters that are now in a character array, figure out what its ASCII value is, so its internal representation as a number, subtract 48 from it, because that's where 0 starts, and then they go 0, 1, 2, 3, and that will give you its digit. We then turn each of those into what the appropriate internal number it is. So now we have a array of my internal representation of them all. Then we take all of those and multiply each individual one, and it's not really a multiply, it's kind of doing, it is doing it because it has to do it by powers of 10. Multiply them all by the correct power of 10 to move it to the correct digit, and then add them all together. That's what parse does. Fortunately, most y'all don't do parses a lot. Normally, it'll be coming in off the data source. You'll parse it once into an integer because you know it's going to happen. You're good like that. You've got it internally. We can kill time to do it once. Everything's happy there. Right? But now we have to do the inverse of this for toString. How many of you all just have some number, you're going to write it out 10 times, you just let it convert every time for it without a care in the world, all that other good stuff, and don't think about what it's doing to actually do that toString. We now need to do the reverse of this algorithm. By the way, this is also why this operator was created, because it's used a lot. So remember this inefficient thing we already created? Yeah, now we're going to use it per digit. Because what toString does is it takes the number, and this is, I'm almost apologetic with how nasty this code is. Sorry. First of all, I have a bail point. If it's a 0, just throw out a 0, because this thing is inefficient. What it basically does is it takes my internal representation of a number. It divides and does a modulo by 10 so that it pulls off the lowest digit and then also shifts everything over. It converts that number it got into the correct alphanumeric character digit and adds it to a string, and then it repeats that for every single one. So it has to go through every single one, do a division by 10 and a multiplication and a modulo by 10, which fortunately I optimized down to one operation. Take those two results, write the character out for one, take the other one, go back into it recursive, do it again until we've done the whole thing, and then we have to build the list back up. That's how toString works. So every time you all think you don't care, not accusing anyone, every time you all think you don't care and you've got this 7-digit number that you're going to print out to the screen multiple times without maybe converting it to a string once and then pasting that string out a bunch of times, this is the operation the computer has to do every time. Fortunately, the .NET compiler is kind of smart. If you have optimization turns on, it kind of sees you're doing this in the background and does it for you. But you really can't assume it's going to be doing this, especially if you go to a different language, which is all going to do the exact same things, etc., etc. This is why kind of knowing how these things work in the background to be able to write efficient code comes really in handy. Now, keep in mind, when you're talking about this and avoiding doing this multiple times, yes, you're in micro-optimization realms, right? You're at the I really have to shave milliseconds and nanoseconds off this routine for whatever reason. But keeping these types of ideas conscious in your head, being able to think like how the computer thinks, putting all of this together will help you think how to write better code in the first place so that you don't have to do all of this stuff, which is hopefully the takeaway I'm getting with all of this stuff. I went all the way to the end. So with that, I am... and then I did all that and I hit the wrong button. So with all that, I'm at peace with everything I was going to say. Thank you all for sitting here and watching and being a part. If you have any questions, let's talk about them. We'll deal the best we can through it. There's all my information right there. I'm on Twitter, Freestyle Coder. I'm not on LinkedIn because I enjoy happiness. I'm not on Facebook because I enjoy happiness. There's my email address. There's my GitHub. I stream on Twitch. I do coding streams. The schedule on that's changing right now, but I'll do some live coding. You can come hack on some stuff with me, including that project if you're interested occasionally. Also, I do some gaming on the weekends. Come join me, and there's all the conference information. Thank you all very much.
Awesome. Well, Chris, appreciate you hanging out with us this afternoon or evening, wherever folks are in the world.
Yeah, we can't assume.
So, chat. Feel free to take a moment or two if you have any last-minute questions for Chris. Drop them in the chat where you are. If not, we'll let Chris get on with his evening.
Oh, I'm gonna leave that stuff open for a second. But I said I would tell you the exact days of DevSpace once I got out of PowerPoint. You come up here so that y'all still need my contact information. There it is.
Mm-hmm.
But close all that. Should be September 8th and 9th.
Okay.
So that should be the dates.
Yeah. All right. Here's hoping there's no more variants.
Yes, here's hoping everything comes. Hopefully that's 1:05 p.m. and not a.m. Surly Dev. Hopefully.
I think Surly Dev's over in the UK.
Yeah.
Yeah.
Well, I appreciate you hanging out. Thank you very much. I appreciate that.
Surly Dev is the best cheerleader for all of us on Twitch.
Awesome analogies. Thank. I really took some time to try to think how to break this stuff down, and that comes back into like at the beginning, learning how to effectively communicate. And I think people underestimate how important that is for programming. When people come to me and they're like, "Hey, I'm thinking about doing a programmer. What's with all this math and all that?" And I tell them, "Look, you don't need to know math. I have a degree in math. It's fine. I love it. I'm a dork like that. Any math you need, they're going to tell you if you can do multiplication, addition, division. You need to know how to break problems down into smaller pieces until you got something small enough you can work with, and you got to know how to communicate to people. And the logical extension is, how do you communicate to your computer as well?"
Yep. All righty. So I don't see any other questions coming in. Thank you, everyone out there on Twitch, YouTube, and LinkedIn for hanging out with us. Thank you, Drew, for hanging out today. We don't have anyone scheduled yet for next month, but we are working on that. So I should actually have that wrapped up by the end of the week. So we'll get that out to everyone once we have it.
As you are currently in the land of speakers.
Yeah. Chris, thank you again for hanging out with us. We were supposed to have Chris last month, and we got lost in communication.
Yeah.
So it's like, well, let's just push it up a month and see what happens.
And we got lost in communication about that NuGet talk. So I'll give me a couple months. I'll come back and I'll do that. I got to get all that stuff set back up again.
No worries. It's all good. And really huge thanks to Disapproving Gorilla for hanging out with us today. All right, friends. We will see you all next month. Thanks again for hanging out with us.